Hello, my name is Josh Brumberg. I'm the Dean for the Sciences here at the Graduate Center. When thinking about the pandemic, we're all looking for some silver linings. And one such example is tonight's webinar, where I can welcome a larger crowd online than we could have hosted in person at the Graduate Center for the start of our fifth season of City of Science event, which kicks off tonight with a fascinating discussion about quantum computing. As a public university, the Graduate Center and its associated Advanced Science Research Center are committed to the idea that our scientific research has a role in advancing the public good. To help us understand quantum computing, what it is, what it means, I'm very happy to introduce tonight's panel. First is Dr. Ismael Faro, who is a distinguished engineer, chief architect of quantum computing cloud and software at IBM. In addition to his work at IBM, Dr. Faro has worked extensively in many businesses outside of IBM, as well as nonprofits and for the government. He is also an avid 3D animator. One day I hope to see one of his films in my local multiplex. Next up is Sara Mouradian, who is currently an intelligence community postdoctoral fellow at the University of California, Berkeley. She is interested in building the robust and scalable quantum systems that are necessary for the next generation of computing, communications, and sensing. She will continue this research as an assistant professor of electrical engineering and computer engineering at the University of Washington. Lastly, leading tonight's discussion is Dr. Gabriele Grosso, an assistant professor of physics here at the Graduate Center and a member of the Photonics Initiative at the Advanced Science Research Center. Dr. Grosso's research focuses on the optical properties of two-dimensional, otherwise known as flat, materials, which show promise for enabling the design and the development of leapfrogging technologies such as quantum information processing systems, which we'll hear about tonight. Before turning over the virtual microphone to Gabriele, a few words about how tonight's event will unfold. Gabriele will lead our panelists into discussion. I'm sure many of you will have questions, which I invite you to submit via the Q&A box, which you'll see at the bottom of your Zoom window. And we will do our best in the latter portions of the event to answer as many questions as possible. My job is done, and I'm going to join all of you in listening to Gabriele and guide us through what I am sure will be a fascinating discussion of quantum computing. Gabriele, the floor is all yours.
I was muted. All right. Good evening, everyone. Of course, before starting, I would like to thank the Graduate Center, in particular Joshua and Karen, for organizing this series of events and for thinking about us for having this informal discussion about quantum computing. So as Joshua just said, today's discussion will be about quantum computing, which is currently one of the hottest area of research. And the reason why is probably why the reason this is a hot area of research is because of its potential impact in the society and in science in general. So the story is that the potential is known and is known to be huge. Unfortunately, we still don't have a device that can give us that impact. So this is one of the aspect that we're going to discuss tonight, but of course this is a discussion about quantum computing, and we cannot start without a famous quote. The quote is from another famous scientist, which is Richard Feynman, and in 1981 he gave a very interesting talk during a conference where for the first time officially he expressed the need for new technology to compute and process information. So the quote is the following: nature isn't classical, damn it. And if you want to make a simulation of nature, you're better making quantum mechanically. And by golly, it's a wonderful problem because it doesn't look so easy. So the reason why I mentioned this quote, not just because it's fancy and everyone does it, is because he already introduced some of the aspects that we are going to discuss tonight. First of all, already tells us a little bit what a quantum computer is. And if you listen to the quote, is a computer that uses quantum mechanics to process information in analogy or in comparison or in contrast to classical computers that use classical physics to do the same. And the other aspect is that it's not easy, and we still don't have a mature technology that allows us to have the impact that everyone is talking about. And another small thing that you can grasp from this quote is the kind of problems that quantum computing can actually tackle. And basically, this set of problems that quantum computer can really express its power is the understanding of nature. So if you want to simulate nature, you know that nature works with quantum mechanics. So it's better if you use quantum mechanics instead of using classical mechanics. And these more or less make up the list of the topics that we're going to discuss tonight. A few days ago, the three of us met and made a short list of what we thought could be interesting and meet the expectation of tonight's audience. And because we are scientists, we like to put the outline of our talk up front. So I'm going to give you a short list of this topic that we decided to cover today. Of course, we're going to start with a simple, the simplest definition that we can give about quantum computer, what it is and how it works. And this we're going to bring us to the advantages of quantum computers compared to classical computers. So this impact or this big revolution that everyone is talking about. And then we're going to talk about the state of the art. I think every person, every scientist, physics engineer that works in quantum, at least once a week, gets this question. When can I use a quantum computer? When are we going to have quantum computers? So we're trying to answer this question. It's not an easy question. So we're going to discuss the state of the art, well, basically where we are now and where we want to go with this technology. And when we talk about this, we also need to mention that there are competing platforms, competing technology that are participating to this race. Of course, when the reward is huge, there are a lot of competitors. And the spectrum of competitors is pretty large, and we're going to try to give, of course, a very brief overview since we have some time constraint. And then we're going to talk about this revolution, this strong impact. So what kind of fields will be really impacted by this technology, and how we imagine the society in 20, 30 years, or let's say when the quantum, I don't want to put numbers down now, but like, how do we imagine our society once we will have quantum computers? And of course, when we talk about this, if we have time, we can also talk a little bit about money. So what kind of business application we can expect for that? And I think this is another question that many of us get very often. How can I make money out of quantum computer? I don't know how to answer this question. Without any further ado, I think we can get started. Oh, one last thing. We're going to discuss and for 45 minutes, more or less. Then, as Joshua said, we're going to take questions that you can write in the Q&A section here. And we're going to close everything and finish in around 1 hour. So I think we can start with Ismael giving us a brief and very simple definition and explanation about quantum computer.
Thank you, Gabriel. Yeah, I go to share my screen and I go to show to you some kind of very simple pictures and graphs that try to simplify how work the quantum computer and what is this quantum computer. This picture that you see here is one of our quantum systems in IBM that we build and we deploy around the world, several of them. The thing that you see here in the middle, all these cables and all these things is the elements that need to handle the particles that we use to make this computation. Finally, the thing that we're looking for is use these machines to, like very well Gabriel said, handle or manipulate the nature, the particles, to simulate and use the advantage of quantum mechanics to make simulations or other calculations that the classical computers cannot affront or cannot achieve. No? And for do that, we try to take advantage of two different effects or two different characteristics of these quantum mechanics. That is what happened with the particles and how we can manipulate the particles. No? And there are two things that is very important for us. One of them is the quantum superposition. That this means is like how you can take a particle and manipulate the particle, the state of this particle, to have the capability to handle more information or manipulate more information than the way that we have nowadays with your classical computers, no? With your phones or your laptops. No? To try to simplify that, is like in the left side, you can see that in your computer, nowadays you work with bits. This means every time that you talk or you write something in your laptop, it's like everything is converted in zeros and ones, okay? And every of these cells, these zeros and ones, these bits, only can have one of these values in the same time. This means you can put a 0 or you can put a 1, but you can never put the both in the same time. And that is one of the first advantage of these quantum computers. In the quantum computers, we talk about these qubits. The qubit is the minimum element that we can handle to can keep this information in different states. This means we can keep 1, we can keep 0, or we can have some kind of intermediate representation between this 0 or 1. This means we can keep different states in these qubits, and thanks to that, we can handle the information in other ways that we are going to converse after this simple presentation. The other component that is a little bit more crazy, and people continues to fight and discuss about that, is this quantum entanglement. This means in the first characteristic, this superposition, you have one qubit. Thinking now that you have two qubits and you have some kind of way to connect the two qubits, okay, some way, that is this entanglement. And when you manipulate one of these qubits, something happens in the other qubit. The thing is that thanks to that, we can make this manipulation in several of these qubits in the same time. No? To put to you, and why the reason, because I say that it's a little bit tricky or different from the how we can understand this feature about the connect two things and manipulate two things. Is like if from the research point of view you take two particles and you can entangle these two particles, you can manipulate one of them, and after that, thinking in this very basic experiment that you have these two particles and you can separate these two particles very far away. This means you put one particle here and another in the other side of the universe. And when you observe one of these particles, you can see what is the state of the other one. That is something that is tricky. In fact, a lot of very big science people tried or didn't understand or didn't believe in this thing until that the experimental people demonstrate that this is something that works and is how we work with these quantum computers. And don't worry if you don't believe in that. There are a lot of discussion in that. We are going to open the discussion with the rest of the panelists about these things. But this is one feature that make these quantum computers very interesting to try to solve these huge problems related with simulate sample molecules. And this is the last picture that I go to show to you. A lot of people, the first picture is the quantum device that we have done in this moment and the people can use. But to be very honest and realistic, this is our day by day. No, we have quantum computers in our labs that you can see a lot of machines, a lot of cables. This means it's like continues to be something that is in very early state that Gabriele said, we need to continue to figure out and reach out like what are going to be the innovations that allow to us to take advantage of this physical side, okay, to finally with the software and all the algorithms and the theory on top of that can take a real advantage of these quantum computers.
Awesome. Thank you, Ismael, for this introduction. I guess you introduced two of the most important concepts, which are the qubits and entanglement. But you also mentioned something at the very end, which are that this technology is at the very early stage, and there are some technological and technical challenges that we need to solve in order to promote this technology. So maybe we can discuss briefly in practice, what do we have to make? So what is that is blocking us, is limiting us to get this? So I don't know, maybe Sara wants to start on that, or Ismael want to continue. Anyway, feel free to talk whenever you want.
Yeah, I can talk a little bit about the challenges that the systems that I work on face. So I think in general, the challenges can be broken into scaling and coherence. So in some ways, as the Feynman quote alluded to, everything around us is made up of quantum particles, right? So everything around us is made out of atoms, but we don't think about the world around us as quantum. We think about it as classical, right? And so why is that? It's because normally what we see is the average of all these quantum effects that just happen, that can be described, that we have described by these classical equations. And so that kind of brings us to the biggest question that we have, which is, so we want to build these really big quantum systems, but we want to make sure that we're not just measuring messy averages, but that we can really control and measure each of these individual quantum states. So a lot of what we do is try to increase the size of these quantum systems without subsequently increasing the decoherence. And so what that means is increasing the ways that the classical world can sneak in and interact with our quantum bits. So I work with trapped ions. It's a different system than the system that Ismael showed. Our systems look kind of like this. They're like a centimeter in size, kind of, and we trap individual ionized atoms inside there. And the biggest thing that I do on a day-to-day basis is try to get rid of environmental imperfections. So trying to shield my systems from magnetic fields, shield my systems from temperatures, shield my systems from, laser noise. And then if I can shield it well enough, I try to control the system and read out the system. And that then becomes like an electronics challenge. So in the end, we still need really good classical computers to be able to change the state of these quantum systems, read out the state, and then take that information and do something with it and feedback on our quantum system. So I think for me, a lot of the challenges are electronics and just shielding of all sorts.
I would like to add that I agree 100% with Sara. It's like this is because finally we don't have the physical thing. Everything that you try to put in the top doesn't work. No? I agree 100%. The physical thing, the challenge to the scalability and the noise of these devices is something that we need to work, or the researchers continue to work very hard. And from the other side is like, what are going to be the algorithms? How are going to be connect the classical side very well, like Sara said, no? It's like finally the world around of these quantum computers is classical computers. All the information, all the videos in YouTube, this video in Zoom, all this information is classical information. How we are going to convert, or what algorithms we need to discover or research or work on to be sure that we can connect the both sides, no? The classical side and the quantum side in a better way. No? That is another big challenge, no? Because there are algorithms, but there are not a lot of algorithms because, again, it's like we are in the beginning of this race, and this is a very long term. No?
That's awesome. So yeah, I think for the first time we heard the word coherence and decoherence, right? So maybe can explain a little bit what this means. So in a nutshell, when you have a quantum computer, you basically want to prepare your qubits that Ismael described in a particular state. You want to give it a color, all right? And you need to give this color to all your qubits. But then we have the problem of nature. And nature wants to change that color because usually these qubits that you use are extremely sensitive and they interact with everything, with light, with other atoms, with electrons, with everything you can imagine. And this is your enemy. And this is what Sara was describing before. So she needs to protect nature from nature, which sounds like crazy. But this is the big challenge. So decoherence is exactly this process where you give a color to your qubit, you turn around, go for a coffee, and the qubit is a different color, and not only a different color, but it's a large variety of colors that mess up completely your previous effort. So this is a very simple definition of decoherence, but this is probably one of the biggest challenges, together with scalability and programming, and combining the fact that now if we want to use a quantum computer, we have to deal with quantum mechanics, but then the rest is classical. So one other big field here is these connectors, interconnect, that take the information out of the quantum computer and make it useful for our world. And this is something that maybe we can discuss in the impact of this field, because as it usually happens when you have a new technology, then you have to shape the world around it, or actually the world around it shape it automatically. So very good. So I guess now that we know what a quantum computer is, we know what a quantum scientist does, we can talk about the reason why we're doing it. I guess Ismael already mentioned that about the power of quantum computer, which is actually this quantum revolution that you can read in the news. So what is exactly that we're going to gain from this machine? You can find plenty of numbers online. I found recently the example, I mean, not recently, but one of the most popular example is the caffeine molecule, and people have numbers that tells you, that explain you the power of that. So whoever, Sara or Ismael, want to say something about the advantages, like maybe providing some examples, and so that everyone can understand what kind of revolution we're talking about.
I want to put one example related with the classical computation again, to try to put a very simple example that all the people can understand in a very simple way. The example that I try to use all the time is the amount of memory that you need, in your classical computer. Nowadays, it's easy to buy a computer that you need to have 16 or 32 gigabytes of memory. If you have 32 gigabytes of memory, okay, making a very basic quantum simulation, okay, in your computer you can simulate around of 32 qubits, no? It's more or less, okay, 32 qubits. The problem is, like, every time that you add a new qubit in this equation, okay, you need to have the double of the memory. This means to simulate 33 qubits, you need to have 64 gigabytes of memory. If you need to execute one simulation in your laptop about the 34 qubits, you need to have 128 gigabytes of memory. And only thinking in that, you can understand that if you have something near to 55, 60 qubits, the amount of memory that you are going to need is so huge, okay, to try to represent the state that this quantum computer can handle. And this is one of the advantages. Thinking again, if you have the capability to, in one of these devices, handle thousands and thousands of gigabytes or terabytes of memory, okay, in this way, this is one of the capabilities that, from the classical point of view, is simple to understand. That, wow, it's like thinking in the data center that you need to have to try to simulate one quantum computer. And entering that is, and connected with your explanation, is like thinking that for simulate chemistry like chemistry to make chemistry simulations, like your molecule about caffeine, you need to have big HPC computers. This means high performance computers. That is some data centers that have a lot of classical computers to try to make these simulations. And like I said before, if you have the capability to put in one of these tubes or one of the devices that Sara has behind, you have the capability to handle these 60, 100 or this number of qubits. These are going to allow to us to explore new ways to make computation, thanks to these capabilities that can bring to us the advantage of simulate more complex molecules. Because nowadays it's impossible in one data center to try to simulate the caffeine. This is the most classical example that the people try to do.
Yeah, I think if I'm not wrong, like to simulate the ground state of the caffeine molecule, you need as many bits as the atoms in the universe, or like more bits than the atoms in the universe, or something like that.
Yeah,
So,
because it's around the 300 qubits, with 300 qubits in the ideal world, not in the current situation, but in the ideal world, yeah, you can simulate all the atoms in the universe. No, the researchers made this calculation and say, oh yeah, we can do that.
I think that brings up a good point. Like, I don't know if people in the audience have heard about the quantum advantage demonstration recently, where Google and then more recently some groups in China have shown that like a quantum computer can do something that a classical computer can. And in some ways, the thing that it did was not particularly interesting to, an everyday person or even most scientists, I think. But what's interesting is that quantum computer is so small, right? It's kind of like an abacus, like one of the first, like a very, very, very small and stupid quantum computer, but it was able to outperform like the biggest classical computing architecture existing today. And so you can kind of get a gauge of the power of quantum computers by that. If we're able to make larger and more robust systems, one can hope we can start solving interesting things. And I think, as both of the other panelists have said, these molecules, clearly there is a lot of simulations that we can do with quantum computers that we won't be able to do with classical computers. But I also think that we will probably continue to find new applications as we start to be able to play with these quantum systems. Because right now the theorists are itching to get their hands on real quantum systems, and we're only just now being able to provide that, I think.
absolutely. How will video games look like on a quantum computer? I got this question asked once and I couldn't answer.
We have someone in our team that makes some kind of games with quantum computers. Obviously, it's like thinking in the first games, the Pong game and all these games that coming from, I don't know, the 70s. Obviously, the games that we try to do is these small, simple games. But yeah, I don't know in the future how these guys are going to show.
Okay, yeah, talking about this, I think I was going to talk about this later, but we're already discussing this. So practically, so we know that we will be able potentially to simulate molecules that now require basically infinite time with the supercomputer that we have nowadays. So this capability it's huge, and I think many people, I mean, like not many people, but like common people don't realize the impact of that in, for example, in the pharmaceutical or the health industry or something like this. Having the capability of simulating what a molecule does and how molecules combine together, this is the building block of medicine or the drugs that we're taking.
Yeah.
Right? So this is probably one of the aspects that touch the majority of the population. So, and this is just one. There are many others. So I don't know if you would like to add something on this list or say something about that.
Yeah, I mean, a lot of medicines now work by, try to find some protein that binds onto a different protein. And the way that people do that now is either with a little bit of computational work, but mostly just trying a bunch of things, like doing huge assays, trying to go over thousands of molecules to narrow down what could work the best. And it would just be much quicker, and we could find more personalized solutions to health problems if we could just simulate exactly how these proteins fold and interact with each other. Not saying that that's going to happen anytime soon on a quantum computer, but
the thing that we are repeating the most tonight is not like, hey, don't expect tomorrow.
Other field that are going to have a lot of impact is the artificial intelligence. And why the artificial intelligence is because you see how work the current algorithms that try to looking for solve these machine learning problems. Like most of them, the idea behind is reduce the energy itself. Because finally the error, like when you put example, you take some kind of machine learning model that identify cats or does, the thing that try to do is minimize the error. This means the difference between the input and the knowledge that have the model, and this reduce the error, that is noise, that is energy, is something that match very well with the quantum computers itself, no? Because finally, like Gabriel mentioned it, is like something that happens automatically in the quantum computers, is like try to go to this state that is the ground state, that is go to zero, and use these capabilities plus other functionalities, ideas related with how take advantage of quantum computers in the AI space is something that is a lot of researchers working on that. No?
And I guess this is probably going to be huge. Already there is a lot of talking about artificial intelligence and the ethics of artificial intelligence with the power that it has right now. So I cannot even imagine what it would be capable of with the boost of quantum computing. But I guess this discussion is left for scientists and machine learning stuff. So, okay, I guess since we mentioned it so many times and we put it up front, all of us say that this is not happening anytime soon. I guess our audience will be interested and curious to know the state of the art. Where are we now? And where do we want to go? And how long is gonna take?
Well, I can talk about trapped ions. So, and I think it's similar for many systems, but right now we can have on the order of, and by we, I mean the best groups in the world can have, which doesn't include me, but you know, the best group in the world can have tens of qubits. I'll say that the average trapped ion group can have like 5 qubits, but we can have like tens of qubits and we can control them. And in the end, to do some of these calculations that we've been talking about, we would need on the order of millions, if not more, qubits. So we have many orders of magnitude left to go.
Yeah,
I would like to hear your opinion on the time scale to reach this million trapped ion qubit.
Good question. I think it's always hard to say, because there's always more. I think there have been a lot of people who have said 10 years over the last, 3 decades since quantum computing was kind of formalized. So it's hard to say, but let's say between 10 and 50 years.
Hey, I got to be a little bit more aggressive because I come in from the business point of view. And in our side, it's public that our team made public that our roadmap is to have this year 100 qubits under control, the next year 400, and in 2023, the ideal situation for us is to have 1,000 qubits under control. Again, be careful because it is 1,000 qubits, like Sara commented, is the current qubits that we have. That is something that is the first version of this qubit, that to try to be more simple, say this thing, you need to aggregate some of these qubits to try to remove some kind of errors using something that we call error correction, and try to figure out better ways to handle the qubits and have better accuracy and allow to us to execute more complex things. Say that obviously, like for me, in the next 5 years, we are going to have some kind of preliminary applications. Okay, when I say preliminary, again, it's like are going to continue to be in the state of the art, but it's something that are going to be more near to have some real application. No? In this moment, the thing that we have, like Sara commented, is like there are some kind of demonstration, but it's not demonstrations that demonstrate the final usability. Demonstrate that we can use the quantum computers to beat the classical computers, big computers, in time. That is great, but we need to looking for real applications. No? In this moment, we are looking for that. No? And that for me are going to be the advantage of this quantum computer, when we can demonstrate that with one quantum computer we can solve something that is useful for the users, no? And for me, it's like between 3 and 5 years we are going to need to start to show things, but something that at the end are going to affect to all of the people that is in the audience today. Yeah, I agree that it's possible that in 10 years, 10 or more years can affect directly more the people, no? Because again, we need to work in the hardware, we need to work in the algorithms and the software to use all of these things. It's a lot of things that we need to put together. But say that, you can see that there are hype because there are a lot of big companies putting a lot of money to try to achieve and demonstrate the usability and the usage of these quantum computers in real problems. And that is the reason, because I believe that, like, I don't know when, but in not very far away, we are going to see the initial preliminary real applications.
Okay, so we have 10, 15 years on one side and 3, 10 years on the business side. Okay, money down. And let's meet again in 10 years, which is the separation between your opinion. Okay, that's great. So I would like to remind the audience that if you have questions, you are more than welcome to add them to the Q&A section here. I see we have already 10, and then in 5, 10 minutes, we're gonna try to answer them. I got a question while you were talking, and when we talk about time, is there, I know that, like, there are many different challenges, like we discussed this already, there is technological scalability and so on, but is there a breakthrough that we change the speed? So let's say the trend now is pretty slow. Is there any scientific breakthrough or technological breakthrough that would speed this up dramatically? Or there are many? If there are many, we can close the question here. If there is only one, I would like to hear your opinion.
I think that, so let's say, maybe let me give 2 answers. Okay. So on a very like technological standpoint, there are, if you could give me a box that was able to shield a space completely from its external environment and had within it, you know, all the controls that we need, then that's a very like nebulous sort of technology, but that would be killer. On a like a related but maybe more specific note, if we were able to find some way to encode quantum information that was naturally separated from the environment, that would also be killer. And that, you know, Microsoft, for instance, is looking into this different type of qubit that has not really been demonstrated like experimentally, but if it were demonstrated, would provide that. So if somebody was able to demonstrate a qubit that just, you know, never decoheres, as Gabriele said, you know, you get a cup of coffee and you come back and your quantum system is different. If you could go on a, you know, a long trip, many years, many days, and nothing happened to your quantum state, that would allow this field to explode.
Yeah, I agree. These fault tolerance are going to be one of the key elements to make a breakthrough. All the teams are fighting, looking for research in that area. Other thing for me is like in the moment that we have better devices, or in any dimension, no, devices with noise, devices without this noise that you commented. In some moment, it's like when we have more qubits and more power, is when I am sure that we are going to open more our minds to reinvent how we can handle these qubits. No, why I say that? No, because this is something that happened with the machine learning in the past. No, and happened several times in the technology in the past. No. The example of the machine learning is like until that we have the power of these GPUs, that is graphic cards, okay? Before of that is like the evolution of the machine learning was, okay, some evolution, but using graphic cards, that is not seeing, it's a graphic card, it's the cards that the people use to play games. It's like using that, there are one breakthrough that was indirectly, that is, okay, we can use these graphic cards to make more mathematics faster, mathematics faster. Thanks to that, thinking in how many, from the algorithmic point of view, how many new advances there are in the last 5 years. No? A lot of people talk now about these generative models or transformers or things that allow to you, example, to generate text like a humans or image like a humans and all of that. That this not happened like 20 years ago, no, or 5 years ago. And that for me is something that can be interesting. No? When we bring to the researchers the capability to have access to more qubits, like what are going to be the solutions that the researchers are going to bring. And I am sure that we are going to have some kind of app killers in that moment. No, now. Now we are restricted to the number of qubits that we have, all the problems that we have. But with the evolution of these qubits, looking for the solution that Sara commented, I am sure that from now to that, we are going to have some kind of interesting achievements that can break through how we can understand the quantum computing itself.
Okay, so basically to summarize, the answer is a magic box that protects you from the environment, or a new kind of qubit that does not communicate or interact with the rest of the world, but can communicate with its peers, right? Mm-hmm. And the thing that Ismael said is basically a change in mindset. So as soon as we can add that capability, that will be a boost by itself, because it will open the mind of scientists and help us to create new devices and find also applications.
I'm going to jump out of the magic box, Gabriele, and thank you, Sara and Ismael, for a great introduction to quantum computing and a really stimulating discussion. And as Gabriele said to all our audience members, if you have questions, please put them in the Q&A, and then we're going to do the best to get to them. We might not ask your question specifically because you might not be able to see it, but I could see there's several overlaps. So we're going to try to get to the topic areas. And first and foremost, there's been a lot of questions about what are the implications on quantum computing on cybersecurity, on cryptocurrency. Is someone going to be able to break the blockchain, get all the Bitcoin? So what is the thinking about how this is going to impact network security and cryptocurrency?
Who wants to take this?
I can start. This is the typical question that a lot of people have. No, it's like quantum computing, basics, perfect. The answer, or my point of view, is very, very, very clear. No, all time that we try to break something, believe me, that there are the same number of people try to looking for what are going to be the next algorithm, the next way to cover the problem, no? Because this coming from the very famous researcher that is the Peter Shor, that thanks to one algorithm that Peter Shor defined and discovered, it like can break this idea that how all the modern cryptography is executed, no? But say that in the same moment that this happened, believe me, there are a lot of people working in how solve this problem in the same way that happened in the classical computation. In the classical computation, you see how many times the people break the cryptographic challenge that we put to try to cover our when you browse in your mobile phone or in your browser. It's like this happened in classical, these are going to happen in quantum, and again, there are people that is looking for the next solutions to do that.
I would like to add something to this. I totally agree with Ismael. And one of the reasons that the cybersecurity is a risk is because we have more computational power, so we can break password much easily. So the protocols that we use now will be obsolete because of the power that we will have. There is the other side of the coin, that quantum mechanics provides a new way to share information in a secure way, and is quantum information theory, which is, let's say, a parallel field, if not a spin-off of quantum computing. So this will basically tell us that we can exploit quantum mechanics to exchange information in a way more secure way. So in some sense, like related to what Ismael was saying, there is already a partial solution to this. And this works basically that you can share information with a key. And if someone sniffs your information and breaks this chain, you know immediately and you can stop the communication. So, and this is intrinsically more powerful than the communication we're using now. And banks and financial institutes are already using this protocol. So we already live in this reality, even though many people they're not aware about that.
All right. Another question is kind of going back to the basics here. You know, quantum physics. The idea was that it was probabilistic as opposed to getting to an exact solution. So, does quantum computing actually give you an exact solution, or just compute the probability of something happening?
I can take a stab at it, but that's a really good question. And what you try to do in a quantum computing algorithm is make it so all of the probabilities interfere in a way such that your answer, or the correct answer to your question, becomes most probable, hopefully with a probability of 1.
Yeah, this is very similar, from my point of view, is very similar to when you compare quantum computing again and machine learning. No? In machine learning, when you have a model, you never have 1 or 0. It's like you have a probability that this is a cat or this is a dog. In the quantum computer, we use with this uncertainty, but again, it's something that we know, and like Sara very well said, we try to use this capability of the interference to reach out what is the most probable, like what is the best answer in each case.
So in your diagram, Ismael, of qubits showing that they can have both states simultaneously, is there a limit to how many states they can occupy at one time?
In principle, it's like from the theory point of view, the people are going to say to you no. From the real point of view, finally, you need to have the measure, get the results, and the limit is the amount of time that you can observe or you can repeat the observation, no? to understand what is the state of this qubit.
All right, and then one of the other things I was thinking about when you were talking about, and this is personal preference. Now I get to ask a question. Is you were saying, when are we going to see this? 10 years, 50 years, whatever it is. And I was wondering if you could contrast that to Moore's law. For those that aren't familiar, it's a very famous principle in computer science that the number of transistors or computing elements within a computer chip doubles about every 2 years, and it's been basically a linear relationship since the mid 60s. And every time we think we're going to reach a limit, we get above it. Is there a way of using that to inform how many qubits you can have under control? You were talking, you hope to have 100.
I think qubits already scales like you double the qubits in 1 year. So these things are already faster. Of course, if you compare classical computer, you start from a very huge number. So if you double, it's a huge number. Now we started with 1 qubit. So the next year was 2 qubits. So we're starting from very low numbers. So doubling every year, the rate is faster, but the numbers is way lower than that.
Yeah. I go to say this again to try to connect this with classical computation. No? In the classical computation, you have the data that you store and you have the data that you process. The big problem that we have is in both sides. No, but the most problematic thing is when you try to move the data from where you store where you made the process. No, and the limitation is more in the time that you try to process the thing. No. In the quantum computer, we are going to have the same problem because, like I said in the beginning, all the data is in classical thing, and you need to convert all these things in quantum thing. But for make this conversion, you need to use classical computers in the middle. And when you send this to the quantum computer to make these magical operations, at the end you need to get all the information from the quantum computer like very well Sara commented, like you are going to have this distribution of these all probabilistic solutions, and you need to take all of this and bring to the user the final inference. No, I think that is this. Make all this pre-processing and post-processing are going to continue to be are going to be a big deal. And for me, these are going to be one of the small constraints that are going to affect indirectly to this amount of qubits that you are going to control or handle.
One of the interesting question that was posted in the chat was a question of verification, because one of the advantages of quantum computing, as you have detailed, is the ability to perform things that with classical computing are either impossible or takes forever. So how would we know that when the quantum computer gives us the result, that it's the right result? It kind of reminds me of the Hitchhiker's Guide to the End of the Galaxy. The answer was 56, but we didn't quite know what the question was.
This is a huge question that a lot of people are trying to figure out right now. Yeah. You could think of having two quantum computers and you run the same thing on the two and hope that they match. And then beyond that, it's a huge research question. It's on the forefront of, I think, what we know.
I am.
Yeah. Maybe you can start with simple problems that you can find an answer with classical computer. At least you check that your system is working fine, and then you scale it up. Of course, scaling up doesn't give you automatically the certainty that your result will be correct. So
yeah, so something that we try to do in our team is to try to split the problem in small problems and validate, it may partial validations. But again, it's one approach. But again, it's something that is a nightmare for a lot of researchers.
So one thing we didn't cover a lot was, we all kind of know what a computer looks like, and we have our laptops, and Ismael showed us what the IBM device looks like, and we can see as Sara moves her head what the ion trap device. But Gabriele, what do you think ultimately will they be portable? You work a lot on the material side. Are there limitations on the materials that are going to impact ultimately the construction of these devices, or we just don't know yet?
I guess the limitation we have now on the portability is the qubit itself. So for example, the image that Ismael was showing, this fancy
chandelier,
fancy cables that are shiny and look very high tech. This is basically a fridge. The material itself with the qubit is pretty small. I don't know, correct me if I'm wrong. It's in centimeter side.
It's not.
Yeah. So all the rest is basically a huge fridge that keeps your qubit extremely cold. And this is related to what Sara was mentioning at the beginning, because you have to protect it. And temperature is one of your enemies, depending on the qubit you're using. I guess Sara has the same. No, you work at room temperature.
We work at room temperature, but our ions are still cold. It's just they're very locally cold, but it can be at room temperature. But we have enough other stuff to keep us busy.
Yeah.
So in terms of materials, I would say it's more in terms of the kind of qubit that you're using. And one of the biggest challenge now, especially in terms of portability and usability for everyone, is to make a room temperature qubit. This would be maybe one of the possible breakthrough that can speed up the process. This is related to what Sara was saying, like you need qubit that cannot communicate with the rest, but can communicate. And having a qubit at room temperature basically means this, means that it doesn't feel the temperature, doesn't feel the surrounding and environment, is isolated by definition. So in terms of material, yes, you can definitely find a material in the future where you can develop these qubits, and there is a lot of research on this. And the goal is to find a material where you can have your qubit that work at room temperature and at the same time maintain the same coherence property, so they don't lose the information you want them to keep.
Now, of course, the computer is just a machine, and ultimately it's the software that allows you to access the computing power. So I guess I would start with Ismael being at a computer software company, at least that's what we think of it, IBM to some extent, is have they thought about the software side, is it similar to classical? I know when using supercomputers, people had to reconceive the way they programmed their algorithms. Is that the same with quantum computing?
Yeah, we try to do something very similar. In fact, we try to create something like this open quantum assembler that finally is like the assembler. It's very similar to the assembler that you have in your classical machines. And we have Python or other libraries that allow to you with classical language to create these circuits, that is this assembler that we send to the quantum computers. And in the last mile of execution, we convert this assembler in pulses, in our case, in microwave pulses, to handle the devices. This means, obviously, like I said in the beginning, we need to connect these quantum computers with all the classical world. Like to do that, we need to bring classical functionalities or classical tools to the developers to achieve that. Yeah.
All right. Well, I'm going to take this as a moment to thank Sara, Gabriele, and Ismael. Unfortunately, the online audience can't applaud and show their thanks, but I will serve as their proxy to thank all of you for explaining quantum and not getting entangled in any difficult issues. To our audience, we're going to say goodbye. If you enjoyed the City of Science, we hope you can join us on November 17th when we're going to be shifting our focus to urban ecology. And this event will live on YouTube, so we can see if some of the predictions that Sara, Gabriele, and Ismael came through when we reconvene in 10 years. So thank you, everyone. Have a good night and enjoy.
Thank you.
Bye.
Bye.